TJ was supposed to give a talk today, but as we are all affected in one way or the other by the lockdown, he asked to reschedule. So I jumped in. So today I'll talk about how to augment reality from neural cameras to subtle visual guidance. It's actually, for some people in Otago, I basically just a few weeks ago, I gave that talk as an internal talk, because these are some of our latest research results, or results from some research projects. In fact, actually, I have to ask for confidentiality, because actually the second part of the talk is actually something that is still not published, but I still think it's quite quite far into the project, so it's still worth to share. So yeah, let's have a start. So oopsie, and I can't click. Why can't I click? Yeah. First of all, and probably most important, so I hope that all of you are working on their IEEE VR paper. So in case, again, if you haven't heard about it, IEEE VR is next year in Christchurch. We still hope that we can run a hybrid event, like a physical presence, even though we have to acknowledge it's certainly got a bit harder with the recent lockdowns, but we will see. Nevertheless, I hope you're working on your papers, because at least the journal paper deadline is approaching quite rapidly. So it's actually only a few weeks to go. But this is just the marketing blurb at the beginning. So now to the focus of today's talk. I want to today talk about two quite different topics, and the only combining thing is that they both share that they try to answer questions around how do we render augmentations, or how do we display augmentations for augmented reality or for mixed reality. So it's not so much about tracking, it's not so much about the really fundamental idea like last time, where we had these computational classes where we, for example, wanted to help visually impaired people, but it's more today on how can we show augmentations, or how can we show renderings. And again, I said that both of these projects are slightly different, because the first one is focusing more on visual coherence. And this is basically a paper that will appear also in like 2 weeks at ISMA. And the second one is more around visual guidance and how you can do that with augmented reality. And that is unpublished and will hopefully be submitted soon, very soon. In fact, we were targeting Kai, but yeah, we have to do a small study, which is now hard. So let's dive into the first topic, visual coherence. What is visual coherence and why it's important? So the paper title is Neural Cameras, so learning camera characteristics for coherent mixed reality rendering. So what's the general problem? So first of all, coherence in augmented reality is quite important, and is quite a well-investigated problem. So what you can see here, hopefully you can see here the digger, and hopefully regardless of your screen, is what you can easily make out what's real and what's virtual. So and why is that? So why we usually immediately perceive that this digger is probably the virtual, because somehow it stands out from the environment, which is in that case represented by the camera image. So the environment is somehow more blurry, even a bit more edgy, so it has somehow a different resolution. And also the colors are completely different between the background, again, which is representing our physical environment, and actually the augmentation, which is the digger. So this is a picture from George Klein paper, who's working on that. And there he provided lots of examples for this. So again, so I had the digger, but here, for example, also there's a Cartman, or there's text augmentation. And usually it's relatively easy to immediately make out what's real and what's virtual. Because again, there's certain artifacts that are in the camera image representing our real environment, but they're not in the rendering. Yeah. So, and he said, there's a video for that. So this is, again, the Cartman. And again, you see basically also part figure that it's quite different from the remaining camera image, which is somehow blurred, has a lower quality, colors are off, lower resolution, and so on and so forth. So why is that? I already mentioned it. That is because we capture the real world usually with camera. So our real world exhibits certain camera characteristics. So this is again from the George Klein paper. So, and here when we just look at a camera image, we see bending artifacts, we see noise because of the camera, we see certain corner softness, so blur, we see chromatic aberrations. So this is usually these slight rainbow effects. We see effects that result from the Bayer artifact, so from the Bayer pattern, which is part, or the color filter, which is part of the camera. And we see a different, basically, a chroma resolution. So that colors and compared to intensities have a different resolution. And what he back then proposed, that he's in really detail re-implementing the camera pipeline. So what he back then did, he was really for one very specific camera. So that's the Texas Instrument camera that you see up there, which was relatively a standard camera, often used, was a firewire camera. And despite the low quality that you have seen, it was used in a lot of research projects. And what George Klein did back then, he analyzed the lens, he analyzed the Bayer mask, he looked for the specifics of the CCD sensor that was in the camera and of the processing. So that's basically what is then done once the image is captured. And he tried to either find the specifications, so find out how the internals of this camera worked, or he tried to analyze and re-implement that. For example, here there are a couple of the graphs from his paper. He for example, really analyzed the noise behavior from different pixels and different color channels. He was not just analyzing how much noise, but also how is it affecting neighboring pixels, because that's something that's also driven by the Bayer pattern. So at the end, he had like a very good understanding of the internal of the camera, which we normally don't have. And because of that, he was able to basically simulate that. And that's exactly what he did. So that's what you see on the right-hand side. So he coded up in hardware a camera pipeline that is simulating all the specifics of the camera. Yeah, that's simulating the lens, it's simulating the Bayer mask, the CCD sensor, and the video processing. And he applied now this camera pipeline to all the renderings. And by doing so, what he's actually doing is, instead of having this digger and this high quality that clearly stands out, he's somehow applying the camera characteristic to the digger as well. And this is what you see here. And of course, he's decreasing the quality, but actually by doing so, the digger now nicely or more nicely blends in with the background. Okay, so there are a couple of other examples. Again, here, South Park figure. Now, if you apply the camera simulation on the virtual content, it gets more blurred, it gets more noisy. The color is worse, and you see actually also the blur is non-uniform, so it's more blurry in the corners. Yeah, again, here a couple of examples. So these are all from George Klein's paper. The problem is that first problem is since then, so this work, I really like this work. I think it's really cool work. That's from 2010, but since then, not so much was going on. It's the first problem. So there could be improvement, but we haven't seen much. The other problem is that George Klein paper is, while really good, is extremely constrained to that one specific camera. So basically, if you use another camera, which is very likely because that is nowadays a very outdated camera. For example, if you want to simulate it for your phone's camera, or we have lots of different phones, then you need to find out the internals of the camera, which is often very hard because often it's like a black box. And that means you need to somehow analyze and really reverse engineering the full pipeline, including lens, all the internals that are hardware, as well as the software, which is the video processing. And this is, of course, not really feasible. And that makes the approach by George Klein not very applicable in practice. Because while the results show, again, while I go back, that we get a more coherent scene, which makes it harder to say which one is real and which one is virtual, it's very hard to make it now to apply for new cameras. And that was actually the starting point for our work. So this is a collaboration with a long-term collaborator from where I did my PhD, so Graz University of Technology, Dennis Kalkhofen's group. And with them, we were working on this. And the idea is actually now to replace that very accurate simulation that is basically reverse engineering. So basically, our idea is that we capture a scene, with a camera, with a real camera. Again, the camera is made of the lens, sensor, and ISP. But we think we are not able to reverse engineers, or we don't have all the specifics that are needed to reverse engineers. So our approach is that we have an initial rendering, and then that we actually want to learn the camera characteristics. So that we want to learn what is actually making or characterizing that lens, that we want to learn what is characterizing the specific of that sensor, and actually of the processing, which is then done on a chip. Yeah, and we want to apply then these learned characteristics to an initial relatively high quality rendering to make it visually more coherent with the rest of the world, which is captured usually with the camera, with the same camera. Okay, so basically the idea is that you don't need the specifics, but that we just need image material that is shot with the camera, and that we learn the characteristics of that camera and use it for visual coherence. So let's talk a bit about that. So how will this, on a high level, how will this look like? So again, that's the expected result. We have an initial rendering. We want to apply these effects, and at the end, our virtual object shares the characteristic of the real camera. So let's look first at the lens effects. So what have we done? So actually, we created a network and we wanted to learn the lens characteristics. That of course required to actually that we capture image material with that camera, and we did this with a specific pattern. And we analyzed basically the sharpness. And so basically, I will not go into much detail, but basically this learning, someone has its camera, sorry, its microphone on. Not sure if we can mute it, or if Alex can mute it. Yeah. So basically, and this approach is what we call LensNet. So we have a custom network that is actually learning at the end the parameter basically for Gaussian blur, and this one we can then apply later to the to our target images. Yeah. So and you see it here. These are just some results on the right hand side. So basically, where we see the generated blur. So this is something actually which is from an image which was in focus, but we simulate the blur that would be exhibited by the lens, because it was more, for example, at the corners, and there is a general softness in the corners for most of the lenses. Okay, so at that point we learned the blur and of that lens by approximating, or by learning actually the parameter of the Gaussian blur function. So, but this is only the first step. Okay, we analyzed that. Actually, here are a couple of more results. We analyzed that against, and we compare it with different blur functions to find out which one the best was, also in comparison to the real lens. And we did this, I refer to the paper here, for actually different cameras to actually show that we can really generalize that. And you can see here, when you actually go on the results of our LensNet, that actually the virtual at that point is from the blur and from the softness is almost impossible to differentiate the virtual from actually real capture with the lens. Yeah, I should say here that all these toy figures, the toy tigers and lions that we see here, that we had a real 3D model of that, and we took 3D scans of that and were augmenting them onto the scene by after removing the real one. So we had a very good comparison on very good data set that we can use for comparison. But of course, if you have a camera, then the lens is only one factor, but the sensor is another one, because every sensor has a different resolution, has a different Bayer pattern, and has in particular also a very different noise function. So the next part was that we wanted to understand the Bayer pattern and how color is received, and wanted to approximate this, and also wanted to approximate noise, which is a characteristics of that sensor. So similarly, we had another network that we trained, and here at the end, it was basically mapping at the end. It was input RGB values together with an ISO and an exposure, and was mapping that to output RGB values that were exhibiting certain color characteristics of that sensor, as well as the same noise. And some results of that is what you see on the right-hand side. So the first one is what we naive. So what we see here, that's basically the A1, the center column. So but what you see here, so you see colored rectangles, and these are real captured with the camera. And then we, that's from a color chart, and we augmented that. So the inner rectangle or the inner cube that you can see is exactly the same color, just overlaid or augmented on top of that. And what you see here, that basically that inner rectangle and the outer one, you can clearly differentiate it because the colors are completely different and the noise is very different. So, but if you already see, so B, if you go to the next row, column, what you see there is that actually, if we do a color correction, then it's already very hard to differentiate basically that inner part, which is augmented or overlaid from the background one, because we already learned the color and match and map to the correct color. But the problem is, if you just do a color and if you do not learn the noise, then at higher ISO settings, so here ISO 1250, then you would still again, or you would again see the inner rectangles because they don't exhibit the color, the noise. So basically what we would need to do, and that's what we did, we learned the color and the noise as well, and then you see some results from different ISO and exposure values that see that now actually it's almost impossible to make out these inner rectangles which are augmented. Yeah, so they are basically they are augmented on a background of exactly the same color. Yeah, and these are some, we did it actually for several color charts, but I refer you to the paper which will appear in 2 weeks or a bit more than 2 weeks. What is important here is to say is that the sensor we were learning on raw images, so not JPEG, but we were learning the raw images, which is the result of that sensor. And we had a dedicated other step that is then actually learning the denoising, which is then usually happening on an image signal processor on the ISP, as well as any kind of other processing that is going on, maybe sharpening, maybe also a slight blur, maybe a small color correction. So basically we learned here the conversion from raw to the actual image that you normally get from the camera. And which is normally done on the ISP. So again, here we used, we had a small network, but here we used some prior work because there were some people before that looking into that. So there is an archive paper from Gao, a very recent one that also did exactly this. So basically they learned the ISP by having a lot of camera images, so the resulting images, but also the raw image data, and they learned actually the raw conversion with everything else with what's going on. Okay, and then once you learned that, you can revert that and actually apply it to raw images to simulate in final output. And this is exactly what we were doing there. Yeah. So again, on the right-hand side, you see some results, and you see basically, as soon as you combine SensorNet and ISPNet, so that is basically, we learn the sensor as well as we learn the raw conversion, then we receive very good results that are almost indistinguishable. There are these small corners which we can correct. This is what you see in D with background. This is where the smallest correction in edge filtering to actually avoid that half a pixel offset, which can still happen, but it's more in the rendering. So basically at that point, when you see in the results D with background, I think at least on my screen, I cannot make out any difference between the superimposed or augmented image patches and the background. Yeah, it's important to say here that we learned the characteristics not on the same data set that we show here for our results. Okay, but we used different color checkers. Okay, so basically our training data set is a different one for our results data set. Okay, so at the end, what you can do, or what we are able to do is, and what we wanted to do is, we wanted to learn the camera characteristic for visual coherence. So again, the idea is that we achieve a higher visual coherence by applying the same camera imperfections to actually our virtual rendering. So again, here, this is what you see here. So we have an input frame that is the tiger, and that is, for example, real. There's a tiger in the foreground and a tiger in the background. So if we just look at the tiger in the background, normally when we do a naive one, we can put exactly that 3D scan of the tiger next to it and just render it. And that would, what you see in the top is very much or very easy to make out. It looks entirely different. But if we apply our learned coherence, and that's what you see in the lower part, then there's still a subtle difference because the right-hand side is a bit darker, but it's probably very hard to make out which one is real and virtual because they both look very realistic. On the right-hand side, what you see there is actually where we blend just in stages between real and virtual. So you see on the left-hand side, that part of the small tiger pup is real, but then we blend towards the naive one. That's the really right-hand side. So with the tail, you see the colors are completely different. But again, if we apply our learned visual coherence, that you see that we get a way better approximation of the colors, of the blur, and of the small imperfections that you see there, which makes it whole visually more coherent. Okay, so we had a couple of scenes where we did that, where we had various input frames, and we had basically for all these models, we had a very accurate 3D scan, and we had the real models, and then we can play around with them, and basically we can replace them or make them more realistic. I think I have a video for this in a second, as well as on the right-hand side, we had even more figures and showed how different lighting conditions is also considered. Okay, so I think there's a small video for that. I hope it's showing here. So basically, again, here the background, one is real, one of the tigers, the other one is virtual, and here we apply virtual coherence, and before that, that was not. And you see that effect, yeah. And I will not go into detail because of that video, because I said it before. The other thing, what we did, we were, apart from this qualitative visual results, we also analyzed the error so more quantitatively. And this is what you see here. So we did it for many of these figures in different environments. So basically, always what you see is the left-hand side is the real figure. Then we see our model, or then we see a virtual model with our visual coherence applied, without visual coherence applied, but just correctly lit, and a very naive placement, which is without shadows and without lighting and without visual coherence. And then the bottom, what you see is actually an error. So basically, the more red it is, the larger the error is. And basically what you see, that of course the largest error is in a very naive augmentation. And if you already correctly light it, that of course gives better results because you get better shadows and also the color slightly change and the intensities. But we can again quite drastically improve the error by decreasing it when we apply visual coherence. So this is here by pixel error in the color values between the real and the virtual. Okay. So, and again, there are a bit more details in the paper. So this is again, this is a paper that will appear shortly at ISMA, and we don't claim, and actually we don't even think that we are better than, for example, that paper by George Klein, who did a really almost 100% accurate re-implementation of the whole pipeline. But what it allows here, or what is the difference, is that instead of really re-implementing for each camera, for each lens, for each camera system, the whole pipeline, and really reverse engineers, we try to learn these individual components, which makes it very easier. So at the end, you just need to show a couple of images to the camera that we know of to actually learn all these specific parameters, and then we can apply this visual coherence, and we don't need to know the specifics. Okay? So that's basically the first part what I wanted to talk about, which was visual coherence. Again, very important for augmented reality, and there's more to visual coherence just than to have correct lighting. The other thing is quite a different project. And again, this is still hopefully in the final steps, or we think it's in the final steps. And this is about visual guidance. So here, what's the idea here? Again, it's also how do we show things in augmented reality and how can we use augmented reality? So I was in different contexts briefly talking about this project. So maybe some of you have heard about it, but we haven't shown most of the information that are in today's talk. on the rest of today's talk. So what is it? So I will start with that video, and again, this is normally how I start that. So it's 2 video sequences. That is a paper from Eduardo Veas. That was a Kai paper, I think, in 2011. And what they were doing, they were manipulating videos. And I'm not sure, I try to synchronize them as good as possible, if you can see a difference. Maybe, can someone see a difference? You are more than welcome to unmute yourself. Is there something different? Let's also check if you're still in front of your screen, or if you do cooking, homework, or take care of your little ones, which you're absolutely allowed to do. No one sees a difference. Okay, I will, before it's getting awkward silence.
I think Wei Hong raised his.
Oh, sorry, Wei Hong. Yeah, Wei Hong, then please unmute yourself.
Yeah, I mean, I see it. The window.
Yeah. So what is different? It's
brighter in the right side.
Yeah. So there's actually a bit more going on. That's absolutely correct. So there's actually a bit more going on than just the brightness, but it's one thing. So basically, what these authors from that paper did, what they were changing what we usually call the visual saliency of the video. So they wanted to raise your attention, your focus, and focus you on a specific part, in that case of that video, by just making very subtle changes in the visual saliency. And visual saliency, normally we say it's made out of the color, and in particular out of intensity and contrast. So if something has a higher contrast, and also the colors are usually a bit more brighter, then it has a certain attraction to your eye, and we start to look in there. Yeah, this is basically how we trained and how our perception works. So basically what they were making these really subtle changes, and they called them almost unnoticeable, and they're very subtle in that example. And they claimed, actually, they did study that actually the people then look there more often and almost immediately. There's a bit more to that, so I would take it a bit cautious approach, but this is the general idea. We want to create your attention. We want you to look somewhere. The difference is, so they did it on videos, and basically what they showed is they just had people in front of a screen with the videos played, and I think they also showed them sometimes images, and they had eye trackers that they used to evaluate their results. The starting point for our research is that we wanted to do something similar, so here on a conceptual view, but we wanted to do it with classes. So the idea is we wanted to give you some classes. Of course, in the future, we hope that they have the form factor like these classes, and hopefully look small and lightweight and cool. And with these classes, we want to, in a very subtle way, we wanted to put an emphasis on certain areas. So basically to highlight, we wanted to make you look in there. We wanted to make it without saying, please look there, how it's traditionally often done in AR, when you have these big overlays or highlights or arrows and so on. Okay, so that was the starting point for that research. And without going into all the details, because unfortunately it was way more complex as we initially envisioned, and also some of the results were slightly different than we envisioned. So basically we built prototypes of some classes. And again, the classes, basically, they had a camera that is capturing roughly the world roughly as seen by the eye. And this is what you see on the right-hand side. So this is the camera image, like our environment. So, and practice, it's a bit more complex. So we built different kinds of bench prototypes and mobile prototypes. So bench is actually where you can't really, I mean, you can look through, but normally we place a camera that is looking through for you. Because it's a bit easier to calibrate, and it's a bit easier to run validated studies and reduce some co-founding factors. And we had a mobile prototype for that. So, but basically for both of them, it's the same. The camera is capturing the environment. What you see here, that black and white or grayscale image, is a saliency image. So basically, the brighter that pixel is, the more salient it is. And we see for that specific image, basically, most of the salient areas, they are on the upper left-hand side. Okay, which makes sense because they are more high contrast objects. There are lots of trees that are dark with the foliage, which is a bit brighter. We have the sky, it's generally a bit brighter, which attracts our eye and is more salient. But what we wanted now to do, we wanted to emphasize something that is not very salient. So we wanted to emphasize, for example, that lower right-hand side. So we computed the mask. That's what you see. It's a simple binary mask in that case. And then what you see is D, we computed in real time, basically a compensation image. So that is an image that if we display it in the classes, it aligns with the real world in a way that it changes the saliency of the scene, or that was at least our expectation. And this is how we computed that mask. So as you see, that whole mask looks very off color because it's almost like a negative. But if we now show it in the classes, again, here, this is what you see, and this is emphasized here so that actually you see the difference a bit clearer than before. And the simulations say that actually now you see it, that now the lower right-hand side should be more salient. And if I show it on the large images, so this is roughly how it looks like. Again, this is emphasized here to make it a bit more clearer standing out for this presentation. So that was how it was before, and that's after. So what's actually happening is we blur it. Some image areas become a little bit darker while we emphasize certain other areas to make them more stand out, to give them more contrast, to make them visually more salient. So that is roughly the apparatus or the general idea. So basically, again, you put up the classes and it's emphasized in certain image areas. And we had different hypotheses that we wanted to have answered in user studies. So the first one was basically that basically with our augmented reality saliency modulation, that we can alter this gaze pattern when compared to an unmodified scene. So basically, and we wanted to measure that with basically with measuring the number of fixation in the target areas. So basically our hypothesis was that if we do the saliency modulation, more participants or significant more participants are looking to the target area, okay, compared to an unmodified scene. And our second hypothesis is that actually that we also decreasing the time. So it's not just that they look there, but they're looking there quicker, okay? So that was our second hypothesis. So we had a couple of problems, and this is how to run that study. So the hypotheses were relatively clear, but the problem how to do that study, because it relied basically on measuring gaze. And there we ran into a problem, and I have to say that we submitted that paper earlier and we got a kind of a rejection because the reviewers were not too happy about how we run our study. So what's the problem? So the first problem is we wanted to do it with AR classes and we wanted to measure gaze. So the first approach is you can use something like, for example, here, like it's Pupil Lab, so it's an external eye tracker on a BT300 and can measure the gaze there. What's the advantage of that? The BT300 has very good colors. It has a very good color space, and actually having a good color space of your AR HMD is very important, because if you have really weird colors, and we come to that in a second, then actually also the saliency modulation is really bad, because basically it's like your screen is off, okay? So basically, but the problem is all the AR displays with really good colors don't have good eye tracking or no eye tracking. And then we tried that initially, and then you get really bad gaze data. The other approach, and this is what you see on the right-hand side, we could take, for example, the HoloLens 2, which is a really cool device, has really good eye tracking, has an integrated eye tracker, would probably give us very reliable eye data. But actually, I'm not sure if who of you actually has tried the HoloLens 2. While it's a fantastic device, and there's a lot of really cool technology, the display and the colors are horrible. So here, just if you really have tried the HoloLens 2, you see some pictures here of Carl Guttag's blog, but they're pretty much illustrated. You get lots of these neon effects. The image is really, really, really bad. And the colors are absolutely off, and the color space is very weird. And we were a bit undecided which way to go, because both have clearly drawbacks. So we went for a slightly different approach, which we thought is the best one. So again, here, this is the summary. So basically left side, you get no eye tracking or very unstable eye tracking. And you get also very small field of view, but you have a good display, easy to capture, easy to modify. On the HoloLens side, you have a really problematic display, color space and color rendering is really horrible. It's actually also very hard to capture results through the HoloLens. If you ever wanted to make a photo of a through HoloLens, it's actually not that easy. It's a good photo. HoloLens is also hard to modify, but they have a decent field of view, but they have good eye tracking, integrated good eye tracking. So we went for a different approach, which we thought is good. The reviewers at the moment don't agree with us, and we probably didn't get it along while we went this approach. So what we had is we took our BT300 and we used our bench prototype for our initial evaluation, and we had basically the camera looking through. We made photos with the camera, and they are shown in a VR headset. So we basically used the HTC Vive Pro Eye with integrated eye tracking for the evaluation, but showed actually the image material that was shot through an actually optical see-through head-mounted display. We thought that we get actually the good colors from the BT300, so a very good color space, very good white point, and actually get the good eye tracking from the HTC Vive Eye Pro. And we run the study. So again, the reviewer think we should still run a study through, let's say, a HoloLens, which we think is not so good. But let's look for now on the results using our current study, because that's where we are. So overall, we had actually a couple of studies, overall 30 participants. And in a nutshell, what we saw a significant effect in the number of fixations and time to first fixations. So basically, compared to no augmented saliency change or saliency modulation, the people looked significant more often in that area, and they looked significant quicker in that area. Okay, we have to say that in many cases, actually, before that, the people didn't look there at all. Okay, so that's the first thing. What we also looked into the areas explored. So what we had actually, so maybe I start here actually. So this is one of these gaze patterns that is just an example, but we saw many like this. Basically, we wanted them to look, we slightly emphasized that center where the red rectangle is. And for example, if we didn't modify it, you get a gaze pattern as on the top. And if we modify it for that participant, we got it like shown there. So where relatively quickly this specific participant looked into our target area, which is good. Again, you can visualize it slightly different. Again, here it's now the white circle emphasizing that area where we wanted to look in there. And this is with a heat map. And again, the top one is without our modulation and the bottom one is with our modulation. So again, just emphasizing that they look more often there. But what we actually also wanted to do is the target area. So we can show with our modulation, for example, compared to a very naive augmentation, they still explored also other image areas. Because what we saw in our study is if you, for example, put a rectangle there, which you can still do, and we also investigate this in our study, then the people only looked there, but maybe missed out other important information. While with saliency modulation, they looked there, but still explored the rest, which is actually beneficial for many applications. But what we also found out that the modulation is probably not imperceptible. And there we agree with prior work who was always saying they were going beyond subtle, and they say their modulation is imperceptible. And we think this is actually, it's not realistic. You might achieve it with one very small, this very specifically prepared image material, and we had quite a large set of image material. Maybe for some scenes you can create that, but we think independent of our setups, even for videos, it's probably not possible. Yeah. That is imperceptible, and we think subtle, yes, but not imperceptible. People will see a difference. Okay, so again, so this was just the starting point for the research on modulating the real world, and we think there are many applications. And what you see here, this is a bit more illustrations of what's possible. So let's imagine here that is Alex, who's also working. Jonathan Sutton is also somewhere, so he's working with me on that project. So one of the ideas that we have is almost like it's noise cancellation for the eyes. So imagine here, so Alex with our mobile classes prototype, he is now in a very busy place and somehow he wants to focus. Maybe he has even issues sometimes to focusing and he wants to focus on his screen. And basically with these classes, one possible application would be that you really tone down the rest, that you really basically do like noise cancellation if you think the rest is noise, and basically increase the saliency of areas you want to focus on and decrease it for other areas. Okay. And the other applications is, of course, that's widely described. This is for example, for search tasks. I'm not sure if it's, again, this is still relatively subtle, and I'm not sure if you can see the difference. So again, let's say that Alex would be in the library, is looking for specific books, and instead of seeing arrows where he has to go, or seeing nothing, which is what B2 would be, we slightly, and this is what you see in B3, we slightly increase the saliency of some books in the shelf and decrease the saliency of others. Yeah, and we want to basically make something very attractive to his eye. It's not as like go there, but it's more like something is interesting there. Yeah, so that's the idea. Again, this work is still in progress, but I hope you see that we have already quite promising results, and we're working quite a long time on that. With that, I would want to almost finish my talk to make it also in time, because I know you have probably your next meetings or your kids are around and you have other things to do. Because this year we wanted to talk more about research. So I have just a couple of other slides, what we're currently doing in the lab, different projects, they're in various different stages. So for example, we have project on virtual tourism. This is where we started to quite heavily work on. This is a continuation of the PhD work of Jacob Young, who's also somewhere there and whose partner is still here in the left-hand side video. So he was working on mobile telepresence, connecting different people, in particular in outdoor location. And now we want to pitch that really a bit more towards virtual tourism, so that people from far away can virtually in real time, so not pre-recorded or not exploring reconstructions, but in real time, they can go somewhere else. So this is something where we're going. With Jonathan, we're still working on lots of topics, and actually also with Alex on amplifying human vision using computational classes, which is a bit more related to the saliency modulation I showed you. And it's the same team who's involved, together also with a couple other collaborators. But I talked about this last time. So we're still doing also a lot of work of interaction on the right-hand side. So on the left-hand side, this is from I think 2 years ago, a Kai paper that we have with collaborators from Graz as well, how interaction in AR could look like. Back then we utilized the mobile phone. On the right-hand side, this is a more current project with Benjamin McCarthy, one of our students, where we explore actually really how do people point. So we are really interested in natural pointing, and we have quite a setup to hopefully get our research question asked. One other thing, what I'm currently working on is egocentric vision, where we started to work. So I'm really interested to really compute. I don't want to have a camera here that is seeing the world roughly how I see it, but I really want to simulate how my eye is seeing. So ideally, I would like to have a contact lens in your eye that is capturing the world as your eye sees it. But I think we're probably not just a few years, but a few decades away from that, because there are lots of applications also beyond augmented reality. But basically, I almost want to implant the camera in your eye without implanting the camera in your eye. And we have a couple of ideas how we can do that. And last but here, there's sound here. Last but not least, we're still interested in pervasive augmented reality. I go over this, and light fields. So this is also another work on the left-hand side with Dennis Kalkofen from last year, I think, Kai, where we used light fields in augmented reality. And we have a student who's probably just very embarrassed right now. This is Ryan, who's working with us on light field selfies. So we're really, it's really cool work where we're exploring, this is what you see there, that is not a camera that he's moving like this, but actually he's capturing a couple of images. What you actually see here is a light field rendering. And we explore basically on going a lot more into light fields, because there are many indicators why we think that's the future and of 3D rendering and 3D reconstructions. Yeah, that closes. There was another one. Too many projects. We're still doing presence, and of course, we're still doing applications of virtual augmented reality, in particular in rehabilitation. Lots of projects with Holger. He will talk about it hopefully later. But now we really made it. Thanks for coming. Despite these hard times, I hope you all are well and stay well. don't forget the VR deadline, at least the journal deadline shortly. And there's a conference deadline, conference paper deadline, and a paper deadline, and a workshop deadline later on. I'm now done. I shut up in case you have any questions. And thanks for coming.
Wei Hong. Is that a clap, Wei Hong, or are you asking
Yeah,
a
it's
question?
a clap. It's a clap.
That's clearly a clap. So, Mark, I'm not sure if you unmuted yourself on purpose. Any questions? Just unmute yourself.
Not from me. I just came late. Sorry, I should have muted, but I had another meeting. But I'll watch the recording and see the rest. Look very interesting.
Tobias, I could ask a question if you don't mind.
Yeah, I don't mind at all.
I come from a completely different construct to you. My background is medical simulation, and now obviously in the AR/VR space.
Yep.
And my upbringing over the last 3 decades is around psychological, technical, and educational fidelity. The fidelity that allows us to capture the imagination of the participant, the student or the clinician. This is in healthcare mainly.
Yeah.
To encourage them to suspend disbelief, to buy into that fiction contract, stay immersed, have that sense of presence. And I'm just wondering how this intersects. I'm the end user, so
yeah.
how your work translates across.
That is quite a large gap. I would more than refer to, if you have the chance, actually, we have the recordings from last year. So my colleague, Holger Regenbrecht, who unfortunately couldn't come, because I think he just received his second COVID jab. So he's working with me, but he has the lead and presence a lot. And there we actually really buy in that, and we explore that the concepts of presence, not just in VR, but also in augmented reality. So what makes it believe it, what makes it unbelieve, what is presence, is it believability, what are the important factors? So, so he gave last year a talk, which is on the website. So we recorded that. I forgot the title, but it's clearly something with presence, and Holger Regenbrecht is his name. So he gave 2 talks, and one is on presence, where he talks a bit about the general concepts of presence and the different approaches, also the different approaches how to measure presence, because there's quite a diversity and not necessarily disagreement, but it's quite challenging to make it right. So I'm a bit more AR with my focus, and so at the moment I don't touch that so much for my core research. Again, I don't like to talk so much about research when it's led by other people. What I would like to say is that also with Holger, we're just working, we're just revising an article where it's a bit more conceptually, where we talk about the long-term effect of augmented reality. So let's just imagine that, like, you have classes, if I see it correctly, I have classes. Let's say they become augmented reality, and they are augmented reality classes maybe in 20 years, even in that form factor. And we talk there about the ethical issues, and there are several ethical issues of that, in particular this continuous and long-term augmentation. And one thing is that there's, of course, that issue that if some of the techniques that I presented here, if they are successful and if they can successfully be integrated in classes, that it will be harder for both of us to separate the real and the virtual, right? So that is what is that? What have you experienced? Is that real, or was that just happening because of our classes?
All right, I've stuck my email address in the chat box so that you can link me up with that person.
Yeah. Sorry, just besides having a clinical background, my other area of study was the pedagogy driving the technology. So I'm very social and cognitive constructivist in my approach. So how do we we have deconstruct and reconstruct the way people see reality, or through virtual reality? So it's quite a minefield, but and there's lots of
confounding variables, as you well know, but we're at Monash, we're trying to see this in terms of not only doability, but scalability.
Yeah.
In this new post-pandemic world that we'll be living in.
Yeah.
So we need to reach out and talk to one another, I guess.
Yeah, because you said your constructivist approach, we also had a paper, very different topic actually. This is more learning in VR, but we really broke it down to something really basic that just appeared earlier this year. I can also link it to that. I haven't talked about this. I think Holger maybe talked about that briefly in a different context in the ARIVE lecture series, where it was really about, we really wanted to explore as many about how learning in VR, does it really help, and what does it add?
Yeah.
And so we always, for us, it's always called the Hypercube project, because basically one problem, what you always have, how to compensate for prior knowledge of people.
Yeah.
Yeah, and we basically use that very abstract concept of the hypercube. So basically a cube in 4D that the people have to interact with in VR to actually get our questions with respect to learning in VR answered. And actually we did this because there's a paper from the 70s, which is almost more philosophical. They already promised to get, oh, not promised, but they already proposed to use that hypercube to get some of the almost philosophical questions. How do we learn? How do we get a grasp, a deeper understanding? And they proposed, so they come from almost the philosophy side, almost constructivist side. And it's really crazy. They have a drawing where they drew up basically a study design and a study apparatus completely evolving around VR, how they wanted to do the study. But because the technology was not ready, they never did the study. And actually we wanted to do the study. We had to slightly change it because we thought some flaws in their approach, but it goes a bit into some almost philosophical questions that we want to have answered.
Oh, yeah, well, okay. That's a further longer question, further longer conversation.
Yep, and I can send you that one.
Yeah, they're good. Thanks.
Are there any other questions? It's good if they're just questions for the project I haven't talked about, then this means somehow okay what I talked about. Then I would make only the advertisement. Mark is still here. Mark, if I'm correct, you are the next in line, so that means Mark will give a talk this week, Thursday at 3 p.m.
Yeah,
yep, 3 p.m. I'm already looking forward to that one. So
am I have to write it.
I can't jump in another time on short notice. My daughter will keep me busy. So yeah, if there are really no other questions, please consider IEEE VR and consider Mark's presentation this week, Thursday. Also, the thing is, just before that talk, I updated our webpage. So where we will continue to put the recordings of the talks, but also the slides, if the presenter is okay with that, online as we did last year. So we also still have the ones from last year if you're interested. Yeah.
Can you put your web link in the
Stephanie,
chat?
can you do quickly, or Alex, send it around? Yep, one of them will do it.
Okay, thanks.
Yeah. With that said, take care, stay safe, and see each other at Thursday at 3 p.m. Thanks for coming again.